Thanks for Professor Shi and Professor Tang, and also the organization committee of this symposium. Today, I would like to share you with our latest research. I collaborated with Professor Charles Ng on the sustainable development of cover system by using the recycled construction waste. First of all, I would like to introduce the background information, followed by the research strategy, methodology, and some key findings. Finally, I will draw some conclusion. Currently, nearly 2,000 sanitary landfills and more than 5,000 simple landfills exist in China. The degradation of solid waste pollutes the surface and groundwater, produces odor gas, so that the safety and the long-term reliability of landfill has become more and more important. So nowadays, we also face the challenges of cities saved by solid waste. Nearly 3 billion tons of construction waste produced per year. The storing of construction waste is prone to affect the safety of the infrastructures. According to the closure standards, there requires a final cover system to minimize the leachate generation, gas emission, as well as to prevent the groundwater contamination. Geomembrane is selected as a material to build a final cover system for modern landfills. However, the use of geomembrane easily induces interface stability problems, and it also easily affected by the defense holes and durability of geomembranes. So that the using of geomembranes would definitely increase the maintenance cost of the closure of the landfill. It shows in the bottom three figures. Several billion of US dollars was caused, financial losses was caused due to the failure of geomembrane. So in order to solve the problem taken by geomembrane, alternative cover assessment program led by USBA was carried out in since 1998. Since then, many alternative covers were proposed and investigated. However, those covers only perform well in the arid and semi-arid regions and only sustain under small rainfall of humid climates. Therefore, a 3D landfill cover system was proposed by our group. The cover can work that combines the benefits provided by the upper capillary barrier and the bottom low permeability to prevent the water percolation as well as the gas emission. Previous laboratory tests and field tests have proved the effectiveness of the landfill cover system under humid climates, and also the elimination of the use of geomembrane. But the performance of the landfill cover system using recycled concrete is still unknown and need to be further studied. So to tackle the limitation, this study proposed a multi-dimensional research program including the 1D soil column, 2D flume test, field monitoring, as well as numerical analysis. This slide shows the material property we used in the physical. Fine recycled concrete used as material for the top layer, coarse recycled concrete used for the middle layer, and we get inside used for the bottom layer. From the bottom table, we can find that those materials have very high contrast impermeability, so that it can ensure the performance of the cover system. The 1D test includes 2 soil columns. Each of them combine a 0.4 meter top FRC layer, a 0.2 meter CRC layer, and a 0.4 meter refused soil layer. We also installed tensile meters and some moisture probe to measure the soil suction and volumetric water content changes along the soil. The top boundary of those 2 columns, we set a 0.1 meter constant water height for last for 8 hours to simulate a 16-year return period rainfall of Hong Kong. The bottom boundary was specified as free drainage. This slide shows the mirrored and computed variation of matrix suction in those 2 columns before and after ponding. The mirrored results, the numerical results match the computer results reasonably well. We can find that before the ponding, the initial suction in the grass column is larger than that in the bare one. It is mainly due to the evapotranspiration induced root water uptake in the top layers. The high initial suction corresponds to the lower permeability it can reduce the water infiltration during the ponding. After the ponding, the mirror matrix suction in the bare column reduced significantly, whereas a relative high suction, such as the 0.1 meter and 0.3 meter in the glass column was preserved. So this shows that after rainfall with a return period of 16 years, the capillary barrier in the glass column is still active, while that in the bare column is felt. The results shows that the effect cover system using the cell concrete can enhance the performance of the cover. Use the of the flume model from the right-hand figure. We can find that in order to simulate different rainfall conditions, a rainfall simulator was developed and installed above the cover system. By using this simulator, the rainfall intensity and duration can be regulated. In this study, the rainfall return period is fixed at 100 years in Hong Kong. A return duration was changed from 4 hours to 12 hours. The inclination angle of the cover system was changed from 3 degrees to 18 degrees according to the national standards. 10 meters and one soil moisture probe was also installed in the flume. In this study, we mainly present the main results in the middle section. And also, we also installed a train gauge and some other equipment to measure the water balance components during the test. So this slide shows the left-hand figure shows the comparison between the mirrored and computer soil suction profile during the simulated rainfall. The total depth during the 12-hour rainfall was more than 400 millimeters. As the heavy rainfall studied, the soil suction near the surface was the first to be influenced by the water infiltration, whereas the matrix suction is the middle CRC layer and the bottom layer was not changed after the fall of the rainfall. So with the rainfall continued, lower soil suction returned in the shell depths. This reduction of the suction means the breakthrough of the capillary barrier formed by the top 2 layer of the cell concrete. At this point, the function of the middle layer can transfer from the capillary break to a drainage layer, so that it still can function to reduce the further infiltration into the bottom layer. And from the right-hand figure, we can find that during the initial stage of the rainfall, that means 0 to 6 hours, surface runoff and soil water storage increase linearly as the rainfall continues. But the amount of water storage reached its maximum value at 6 hours. So after that, the infiltrated water started to divert laterally in the top FRC layer and the middle CRC layer. This means that the top 2 layers can function as the drainage layer effectively. During the whole test, no population was observed, even without using a geomembrane. This slide shows our physical test conducted under different rainfall duration from 4 hours to 12 hours, and different inclination angles from 3 degrees to 18 degrees. We can find from the right-hand figure, from the left-hand figure, the longer the rainfall duration, the more water will be infiltrated into the cover system, so that less surface runoff under the longer duration, and less soil water will be over, as well as the lateral diversion. And the intensity will also reduce in a sooner water breakthrough of the top capillary barrier. From the observation for the different inclination angle, surface runoff increased. Can find that surface runoff increased with the increasing of the angle, and the increasing of the angle will also lead to the reduction in the water storage as well as in the lateral diversion. We also carry out some parameter studies to optimum the combination of the particle size we used for the cover system before we use them in the field site. The top left figure shows that the surface runoff decreased sharply due to the D10 of FRC increases from 0.1 millimeter to 0.5 millimeter. So with the first improve of D10 of FRC, the surface runoff reduced gradually to zero, but the rainfall water into the landfill cover would transfer to water storage and infiltrated water into the deep soil layer. As shown in the figure, the surface runoff reduced to less than 15% when D10 of FRC larger than 0.2 millimeter. This meets the recommended criteria by the national standard for the surface runoff of Greenland. However, the D10 of FRC does not influence on the returned and diverted water when the FRC D10 is larger than 0.5 millimeter. So the D10 of the top FRC layer is suggested within the range of 0.2 meter to 0.5 millimeter. As shown from the top right-hand figure, the surface runoff increased with the improvement of the D10 ratio between the FRC and CRC layer from 10 to 100. The reduction in the returned and diverted water is very solid when the D10 ratio increases from 10 to 15. It can be found that the surface runoff returned and diverted water is almost not changed when the D10 ratio increased more than 100. So as a result, the D10 ratio between FRC and CRC layer is recommended as 15. Those combinations can provide sufficient returned and diverted water as well as meet the design criteria. And we also conduct a numerical parameter study on the bottom FRC. In this study, we want to replace all the soil layers in the cover system using FRC. We found that if we want to achieve a better performance to meet the US EPA guideline, the D10 of the bottom FRC is less than 0.02 millimeter. So based on the previous physical test, okay, thank you, as well as the numerical parameter study, we came out with this particle size combination. The top layer we use a coarser FRC. The middle layer we use a coarser CRC. Because for the supplier producers to produce very fine FRC is not credible and also not economically efficient. So we use the 10% bentonite to amend the FRC used as a bottom layer. Here is the instrumentation layout as well as the front view of our field site in the Shenzhen field. We also installed meters, soil moisture probes, and gas pressure sensors, as well as the lysimeter in the field site. The whole field site is around 300 square meters. This slide I will show some construction produce of our field sites. The top one is the bottom layer, the middle layer, as well as the top layer, and also our installation process about the lysimeter, the movement point, as well as the soil moisture probes. So this slide shows the monitor result on the population. Top figure shows the cumulative one during the around 2 years monitoring. We can find that the whole the cumulative population during the 2 years is less than 30 millimeters and definitely lower than the US EPA standards for the 2 years. And the first year population is nearly zero. The second year is close to 6 millimeter. And we also compare the annual population with other type of the cover system, like the capillary barrier, the ED cover, and also our previous studies, so that we can find that when the annual rainfall larger than 1,500 millimeter, the performance of the cover system using RCA is better than other type of the cover system. And I draw some conclusions, find the beneficial of the grass, and also provide the recommendations for the particle combination of the cover system. And the way forward, because of the cover system, the function of the cover system is built on the unsaturated, essentially on the particle size and the hydraulic property of the materials, so that all the materials can crush into the suitable particle size, can be used as a material in the cover system, so that the really bricks, the grass, as well as the fine fraction of the aged municipal solid waste, can also be used in the cover system, because those waste materials are in very large amounts, but their strength is not high, so that it can not be recycled in the construction engineering, such as the road and the buildings. And we also have some other application scenarios, such as the slope stability systems. Our cover system can combine with the plants, as mentioned previously by Professor Liang, and we also localize the green system for the sponge city. So that's all my presentation. Thank you for your attention.